Welcome back to our course on complex analysis. In the previous lectures, we have seen something about the concept of antiderivatives and some problems, some theorems based on it. Now we are going to see Cauchy's theorem. Okay, so this Cauchy's theorem can be proven in two ways. The first way is to make use of the idea of Green's theorem, and the second way is to make use of the Goursat's lemma. Okay, these two will play a very important role in the theory of complex analysis. Okay, first of all, here is the statement of Cauchy's theorem that tells you that a function is analytic and the derivative of the function is continuous at each point of C as well as interior to C, which means what? If you in the region, okay, in the complex plane, if you have this to be your contour, okay, this to be your contour, and each point of C in the sense the points that are on this curve or an arc. Okay, points interior to it means inside this we will have plenty of points. In all these points the function has to be analytic, and the derivative has to be continuous. This is what they mean by the hypothesis. Okay, actually in the hypothesis that is given to us, then integral over that contour C is 0 of any analytic function. So this is what we are about to prove now. Okay, so here the C is specifically a closed contour. Okay, that has to be there. Fine, so let us start the proof formally. So in the proof, let us take C be a simple closed contour. Z equals Z of t with t lying in the interval a to b, okay, which is described in the positive sense. So whenever a curve is said to be described in a positive sense, it means what? It is the direction is in the anti-clockwise. Okay, and we assume f is okay, and actually it is given, right? Is given f is analytic at each point interior to and on C, right? So how can we write about the integral, this integral over C f of z dz? This may be written excuse me, this may be written as integral a to b f of z of t multiplied with z prime of t dt. And if f of z is u of xy plus iota times of v of xy, and z of t is x of t plus iota times of y of t, okay, if it is so, then let me mark this as equation 1. Then the LHS, then the integrand in LHS, sorry, not in LHS, in RHS of equation 1 is a product of two expressions. What are they? Let us examine now. So we'll have to calculate f of z of t multiplied with z prime of t, which is nothing but u of xy plus iota times of v of xy. This is to be multiplied with x prime of t plus iota times of y prime of t. Right? So this is happening. Actually here u is what? U is a function of x and y. They are functions of t. Okay, that we'll have to be very clear with. So this is multiplied with this x prime of t and plus iota times of y prime of t. So when you make this multiplication, I'm just going to write this in a simpler terms. I'll write this as simply u and this as simply v, and this as simply x prime, and this as simply y prime. Okay, since all these are functions of t, I am not explicitly writing t. So when I make the product, what would I get? I would get u x prime minus v y prime plus iota times of v x prime plus uy prime. So this is what we would get, right? Therefore, integral over c f of z dz is integral a to b. What? This quantity is equal to this quantity. Therefore, replacing this with this expression, we would get ux prime minus vy prime plus iota times of vx prime plus uy prime dt, and this may be split into two things, that is integral a to b ux prime minus vy prime dt plus iota times of integral a to b vx prime plus uy prime dt. Okay, so now we mark this as equation 2 and proceed further. Now in terms of line integrals, what are we getting? Line integrals of real valued functions of two variables. Now just forget that these are complex integrals. Okay, you have this iota which is a constant, we take it outside. Now we look at only this integrals. These two are real valued integrals of two variables. Okay, then we make use of the line integral ideology to write this integral a to b u x prime minus v y prime dt as integral a to b u of xy, okay, x prime of t minus v of xy y prime of t. Okay, when I mean by this, in addition I'll have dt as well along with this. So this total quantity I write it as dy and this total quantity I write it as dx. So this becomes integral a to b u dx minus v dy. Okay, similarly integral a to b v x prime plus u y prime dt, this becomes integral a to b v dx plus u dy. Therefore integral over c f of z dz is integral a to b u dx minus v dy plus iota times of integral a to b v dx plus u dy. Okay, so we mark this as equation 3 and we are just going to make some observation here. When we observe, the expression in equation 3 can be obtained formally by replacing f of z equals u plus iv and dz as dx plus iota times of dy. If you just replace here, this is what you are going to get, right? So that actually happened. So we'll proceed further. So this expression 3 is going to be a valid one for any type of contour. Even if it is not a closed contour, this expression is valid. So there is no second thought about it. Okay. Now we pay attention to something. Okay. So suppose that two real valued functions v of xy and q of xy together with their partial derivatives are continuous throughout the closed region. Are by closed region, what I mean the interior points as well as the points on that region, all those things, right? So the closed region R is obtained by considering the points interior to and as well as on C. Okay, by Green's theorem, integral over C pdx plus qdy is double integral over R qx minus py dA. Okay, so now this is a general result. Now we turn our attention to the function that we have here. Uh, the given function f is given to be an analytic function. It means it will have to be continuous as well. Analytic means differentiability is there. Differentiability will imply the continuity, right? So the continuity is there. Also, since the function is analytic and also it is given that the derivative is also continuous, so the requirements are there. Okay, so directly we write by Green's theorem, integral over C f of z dz is double integral over R. Okay, so actually in the, okay, let us write one by one. Okay, integral over C, right? So okay, did I write it right? No, here we'll have to remove the parameterization, so that it is integral over C. When you have the parameter t, you can write like this. Okay, you can write integral a to b. When you remove the parameter, you will have to write over C only. Okay, I made a mistake there. Correct it if you are taking it down. Okay, so integral over C udx minus vdy, this shall be written as double integral over R. First of all, pdx plus qdy. This is the way in which we'll have to consider. What is q? It is minus v. So minus vx, and then by default we have minus here, and the p value is u, uy dA. Okay, and integral over c udy plus, actually what we have is vdx plus udy, right? So this may be written as integral over R ux minus vy dA. So this is what we are getting, right? If I'm not wrong. Thus, okay, now we are just going to make use of the analyticity. F is analytic. This implies Ux is Vy and Vx is minus Uy. This is by CR equations. When this is true, Ux minus Vy is 0, and you can just bring this to this side. So minus Uy minus Vx is 0. Therefore, integral over C udx minus vdy is double integral over r 0 times of dA, which happens to be 0, and integral over C vdx plus udy is also 0. Okay, as a conclusion, what we get is integral over C f of z dc is 0 plus iota times of 0, which happens to be 0. Okay, so finally what we get, this quantity is equal to 0. So this is what we intended to prove in the statement of Cauchy's theorem, right? Okay. So I said the Cauchy's theorem has two versions. One is by using the Green's theorem, another is by using the Goursat's lemma. When we make use of the Goursat's idea to prove that we omit the continuity on f prime. Okay, because the continuity on f prime directly follows from the definition of analyticity. Whenever your function is analytic, that will imply your derivative is continuous. If you have a doubt in it, yes, I leave that as an exercise to you. You can check it out, right? So now, before going to Goursat's lemma, I would like to discuss about example here. Okay, so the example that we will see is, if C is any simple closed contour that may be in either direction, okay, be it on positive direction or negative direction, that doesn't matter here, then we'll have to prove f of c exponential of z cube dz is 0. Okay, that is quite easy to check. What are the things that we'll have to check? The first thing, exponential of z cube is analytic. Okay, this is basically analytic everywhere. The next thing, okay, if we consider this as f of z, then f prime of z is nothing but 3z squared exponential of z cube, which is continuous everywhere. Hence, by Cauchy's theorem, we conclude integral over c exponential of z cube dz is 0. Right? Okay, now let me show you the modified Cauchy-Goursat theorem. Okay, before this we have the actually Goursat's lemma's proof. Okay, this is the Cauchy-Goursat theorem. That is, if a function is analytic at all points interior to as well as on the simple closed contour C, then the integral of the function is 0. Okay, so this is equal to 0. This is the Cauchy-Goursat's theorem statement. But in order to prove this theorem, we need Cauchy-Goursat lemma, and that lemma is this. Here what is given, f is given to be some analytic function throughout a closed region R. Okay, it is clearly said that it is throughout a closed region R, which consists of the points interior to a simple closed contour with the points on the C itself, which means, as I just told you before, if you have this as your simple closed contour, it consists of the points on the contour as well as interior to it. So you are just going to have some region of this sort, right? So, and for any positive number epsilon, usually epsilon means what? It is a very small positive quantity, almost zero, negligible quantity, right? But that epsilon plays a very important role in our mathematics. Yes, of course. Okay, coming back to the lemma, for any positive number epsilon, the region R can be covered with a finite number of squares and partial squares. Okay, what do we mean by squares and partial squares? While proceeding with the proof of the lemma, we will see. Okay, indexed by 1, 2, which means only with the finite number of things we are going to do the thing. Okay, do the requirement such that this quantity is happening to be true. Okay, it means what? It is just the when we take limit z approaches to zz, this to this function, when you take this limit, you are going to get your f prime at zz, right? So that's the same thing, which means what, the differentiability is valid inside the region. That is what we are going to prove, and this property is about to satisfy by all the points in the square or partial square, which means what, the function has to be differentiable at all the points inside a region. That is what they are trying to convey. Okay, so differentiability exists, and if it is satisfying this condition, it means you are fixing a point zz, and for each z in the particular square or a partial square, it has to satisfy, which means analyticity directly gives you the continuity on f prime. That is what we are about to prove in this lemma. But unlike the usual lemmas, this will not involve any, like this will not involve any derivations or something like that. Okay, with the help of pure geometrical idea, we will have to go through this lemma. Okay, okay, and now you might have understand what do we mean by Goursat's lemma. That is in the statement what is given, that you might have understand. Now let us get into the proof. First of all, what should we do is that we'll have to start from, like suppose, okay, as it is specified in the previous slide itself, suppose you have something of this sort. Okay, we draw lines parallel to the axis with equally spaced. Okay, that spacing, it is completely up to you. You can fix the spacing as you want, right? So we draw lines parallel to the real and imaginary axis and try to cover the region with the squares. Okay, here this is a part of a region. Okay, I am taking this square, this is a part of a region, and in the square all the points are inside the region R. Okay, and if you consider this thing, only this part of the square is covered, like only this part of the square covers the point in the region, and the rest of the points are outside the region. So we remove those points which are outside the region, and we call that thing as a partial square. Okay, so that is what given here. First of all, we'll have to form subsets of the region which contains the points interior to C. Okay, in order to do this, we draw lines parallel to real and imaginary axis. Okay, therefore we get a finite number of closed square subregions and all those things. And I said about squares and partial squares, right? So we have that as well here. Okay, Now consider there is some square in which no point Zj exists such that the inequality 1 holds. So here we take this as the inequality 1. Okay, we mark this as inequality 1. We say there is some square in which no point Zj exists, no point, okay, such that it holds for all other points Z in it. Okay, for all points it is not, no point exists, which means suppose, okay, if such thing is there, what should we do? That is the scenario that we are about to discuss. If the subregion is a square, then what do we do is that we then subdivide this region into 4 smaller squares just by joining the midpoints of opposite sides. Okay, if it is a partial square of something like this, we consider the whole square and do the same thing. So after subdividing, you may very well notice these 3 portions do not cover any part of the region, so we consider only this thing. Okay, after splitting this into 4 squares, 4 equal smaller squares, we consider the squares which cover some point of the region, and we discard the remaining part. Okay, so next, again, if in any one of the smaller subregions no such points exist such that the inequality holds for all points in it, we again go on do the same thing. Okay, suppose in this case, suppose this is the square in which it is not happening, we then subdivide this thing. Again, if it is a partial, okay, here also if it is a partial square of this sort, then we do this thing. Okay, we'll have to keep on doing it till the required region is covered by a finite number of squares and partial squares such that the lemma is happening to be true. Suppose, okay, suppose that the points Zj does not exist or do not exist after subdividing one of the original regions into finite number of times, what is going to happen? Okay, so I'm about to stop this lecture by this. You will have to pay attention to what we are doing in this lemma. Okay, try to if you want, you can revisit, you can go backward and see what happened here, right? So try to understand till this. We'll meet in the next lecture and we'll try to complete this lemma as well as the Goursat theorem in the upcoming lecture. Thank you.